Good morning, everyone. Today we're looking at lesson 98 in our textbooks. It's on page 674. You can see by the title here, we're going to be talking about scale and scale factors. In the preceding lesson, we discussed similar triangles. Scale models and scale drawings are just other examples of similar shapes. Scale models and scale drawings are reduced or enlarged renderings of objects, of actual objects. So in other words, if I have a small model airplane, which we're going to be talking about in just a moment, and an actual airplane, we can see that the scale is going to represent how much larger or smaller one object is to another. So just like we talked about with similar triangles, the lengths of corresponding parts of the triangles were proportional, so it is true also of scale models and the objects that they represent. They're also proportional, and we'll see that in just a moment. So let's talk about, first of all, filling in this first part of our lesson up here. The scale of a model is stated as a ratio. Go ahead and fill that in. And then I'm going to scoot down to the bottom of my document. You don't need to take notes on this. I just want you to watch with me for just a moment. You're going to notice I have two American airline airplanes here. The first one on the left, however, is simply a model airplane, and the one on the right is the actual object. It's an actual true-to-life size airplane, American airline airplane. Okay, so in the book, this is an example that's given to us, and I'm going to go through this with you. We're going to see two methods of solving for something here. We are told in this problem that the scale of these objects is 1 to 24. And what that means is that my model is 1 in my ratio, and my actual object, the American airline plane on the right, is 24 times bigger than my model airplane. We are also told that the wingspan, so these are hard to see the wings, but if the wing was out to here and you could see the wing here maybe, the wingspan is from tip to tip. They're saying that that is 18 inches, the wingspan on my model plane. On my true-to-life actual object, I can't see the wing over on the other side, but let's just say it's going back like this. I know that looks kind of like a leg there. I'm not much of an artiste. But from the tip of this one wing to the tip of the other wing, we are supposed to figure out how many feet that is when we know that the scale is 1 to 24. So let's look at one method, and then we're going to look at a second method, and then we're going to actually build an example into our notes as well. Okay, so the first method is we would take our actual airplane part of the ratio, which is 24 times larger. Obviously, the actual object is going to be larger than the model. So the larger number in my ratio represents the part of in my ratio here in my scale. The larger one goes to my actual airplane. So we're going to start off with that. So we would take our 24 times the size of our model airplane. Okay, so let's just kind of figure that out. So I would do 24 times, actually let me turn that around for you. We're going to put our 18 first. I'm going to turn that around and say our 18 inches is going to be increased 24 times the amount. In the end, we want this to be in feet. So I would have to divide that by 12 inches in the end. We can cancel out our inches here. I also see that I can do some canceling between my 12 and my 24. And then what is left is 18 and 2. So my answer would be 36 feet. So the wingspan up here is 36 feet on my actual object. Okay, so 36 is actually 24 times, 36 feet rather, is 24 times my 18-inch wingspan on my model. Now, another way that we can do this that was method 1. Let's look at another method. And I always tend to, me personally, I like the ratio boxes, and that's what method 2 is going to actually be demonstrating here. I like the ratio boxes because I think it's a great way to actually keep your information in an organized fashion. The left side is going to actually be our scale of our model and our object, our actual object. And we said that was 1 to 24. Our object is 24 times larger than our model. And then our measurements that were given are going to be on this second column here. And the model had an 18-inch wingspan, and we were going to try to figure out how many feet the wingspan is in our object, our actual object. And you guys have seen this before. You also know what to do with this. We're going to take what information we have in our ratio box and set up a proportion. So I'm going to have 1 over 24 equals 18 inches over W. And then I'm going to do my cross products. So 1 times W just gives us W here. And then 18 times 24 is going to give us 432. Let me just write this down. So we'd have 18 inches times 24. And that, if you do the math on that, you're going to end up with 432 inches. Well, we're supposed to figure it out in feet. So we need to make a conversion here. So yes, you could take 432 and you could divide that by 12 inches, right? And that'll give you the amount of feet. But we've been working with unit multipliers. And so we're going to actually do that. I'm going to take my 432 inches and multiply it with a unit multiplier. I'm going to have inches on the bottom. We want to go to feet, so feet will be on the top. So 12 inches is 1 foot. We can cross cancel our inches here, and we would end up with 432. Check this out. We end up with the same thing we had up here, 432 divided by 12. So what do we get when we do that? We end up with 36 feet. That's what we had left. 1 times 432 divided by 12 gives us 36 feet. Okay, so we end up with 36 feet on both of those, and that tells us the wingspan right up here of our actual object. Now, we're going to look at a problem together that's going to be built into your notes. We're going to look at example 1. Example 1 says, Sophia is molding a model of a car from clay. The scale of the model is 1 to 36. If the height of the car is 4 feet 6 inches, what should be the height of the model in inches? All right, so the first thing that we need to do is we need to recognize that we're given our scale of the model is 1 to 36. So in our ratio box, we can go ahead and put 1 to 36 down here. Let's go ahead and on the outside, we're going to write model here, just like I did in my airplane one, and then the object here, which represents the actual object. Number 1 back up here in the steps, we need to convert our 4 feet 6 inches to inches. Why? Because we want to find out what the height of the model is in inches. So we need to take the 4 feet 6 inches and turn that into all inches. So how do we do that? We're going to take our 4 feet and multiply it by 12 inches, and then we'll add this 6 inches to it, and that will give us the amount of inches. So we have 48 plus 6, which would give us 54 inches. Okay. So now we know that the actual car is 54 inches, and that would be our object, not our model. It's the model that we're going to try to find out. That's what the question asks us. So we'll put M for model, and we're going to set up our proportion now out to the right-hand side here. We're going to have 1 over 36 equals M over 54. When we calculate this with our cross product, we have 36M equals 54. We would divide by 36 because we want to isolate the variable. On both sides we divide. And when you do the math on this, and actually I'm going to reduce this here. I can tell that both of these can be reduced by 9. I think there might be something bigger, but we're going to just start with 9 and have 6/4. Yep, now I can divide both of those by 2, and I would end up with 3/2, which then would be m is going to be equal to 1 1/2 inches. So the height of my model car is 1.5 or 1.5 inches. And that is the answer to that problem. Okay. Next, we're going to talk about scale factor. Let's go ahead and fill in what the scale factor is, and then we'll discuss it. So the scale factor is the number of times larger or smaller that the terms of one ratio are when compared with the terms of another ratio. And we're going to put an example in here as well. But let's go ahead and fill in those empty blanks. So the scale factor is the number of times larger or smaller that the terms of one ratio are when compared with the terms of the other ratio. An example of that would be if I have a ratio that's 3:4, and I see that it has a ratio that's 18/24, the scale factor is how much larger the second ratio over here is than this one over here. So how much larger is that? Well, how did I get from 3 to 18? Looks like it's 6 times larger. Okay, so the scale factor here is actually, I'm just going to abbreviate that. The scale factor for this one is actually 6 because it's 6 times larger. 18 to 24 is 6 times larger than 3 to 4, or I could say it backwards. I could say 3 to 4, the ratio of 3 to 4 is 6 times smaller than the ratio 18 to 24. But the scale factor is the term that identifies how much smaller or larger one is than the other. Make sense? Okay, so let's look at example 2. So I've got a fraction here, a ratio here of 3 to 7. And I have one over here that is 15 to I don't know what. We have an n here, we have a variable. So we have to figure this out. So when I look at the 3 in relationship to the 15, I try to figure out how much larger 15 is than 3. Well, we would have multiplied by 5. So therefore, n is going to be equal to 35. Whoa. I wonder sometimes if you guys ever get dizzy watching my videos. Sometimes if my hand hits something, a page can just go flying into oblivion. Okay, so n is equal to 35 because 3 over 7 is actually 5 times smaller than this ratio over to the right, which means that this ratio is going to be 5 times bigger than 3 to 7. Okay, you saw how I did that. So what is the scale factor? The scale factor is actually how much larger the second ratio is than the first, which we identified as 5 times. So the scale factor is 5. Let's look at example 3. So in example 3, there's 2 triangles. They're similar. We're going to calculate the scale factor from the smaller triangle to the larger triangle. And they give us a hint here to set up an equation to find the scale factor between the 2 corresponding sides. I'm going to need for you, though, to fill in some information about these triangles. So let me make this a little bit bigger. I'm going to change colors here just for the fun of it. Let's go ahead and put in, these are right triangles. I pulled these out of the book, but it was going to be easier for me, rather than typing in all these numbers, it was easier for me just to have you fill them in. So let me see here. Let me get these out of the book to make sure they're in there. Yes, they are. Okay, so on the smaller triangle, we have one side is 20, the base is 16, and this side is 12. On this one, we have 25 and 20 and 15. Okay, we're going to call this one triangle A, and this one is triangle B. So we're giving them some names here. Okay, now we want to try to figure out what the scale factor is here. And so we have to kind of look at each side. Now remember, they're similar, so that means that my sides are proportional. But the problem is I can't look at any one of my sides that correspond. Like for example, let's look at this. So here's a corresponding side. 20 corresponds with 25. 16 corresponds with 20. And 12 corresponds with 15. But the problem is I can't identify how much larger, I can't quickly figure out what is the scale factor that takes me from 20 to 25 or 16 to 20 or 12 to 15. So I have to kind of think back. How did I, in example 2, what did I do with my first ratio to arrive at my second? Well, I multiplied it with the scale factor. Remember up here? That one was easy to identify. Going from 3 to 15, the scale factor was 5. It's not as easy on this example, in example 3. So, but what I do know is I could take any one of my corresponding sides, and I'm going to choose this one here. I could multiply 20 with the scale factor if I knew it, and I don't, so I'm going to call it F. We're going to multiply 20 times the unknown scale factor, and it's supposed to equal 25. Think about it, just like up here in example 2. I took 3 and I multiplied it with the scale factor to get 15. I'll fill all that in just a little bit. Okay, let's go back down to our problem in example 3. So now I can solve for the scale factor by doing what I know how to do. I'm going to isolate the variable by dividing both sides by 20, because that gives me 1F or F. And then when I do the math here, if I divide 25 divided by 20, I'm going to get 1 5/20, which is actually 1 1/4. So I'm going to get 1 1/4, or we could say 5/4, or however you want to do this. Actually, we could have actually done 5/4 here, even divided this by 5 and reduced it right here to 5/4, but we get 1.25. So the scale factor is 1.25. So that means that triangle A and triangle B, the relationship between those, the scale factor says that triangle B is 1.25 times larger than triangle A, or I could say triangle A is 1.25 times smaller than triangle B. But the scale factor just tells you how much that thing is increased. Okay, so that fills in your notes. There's a couple other things that I'm going to come down here and talk to you about, because I do think there's in your lesson today, I believe that there is a problem like what I'm going to show you here. Okay, let's change colors here so they are separated a bit. Let's pick, let's do green for a change. Okay, let's say I have a cube. Oh no, it's not perfect. It never is. But there's my cube, and let's say each side is 1 centimeter, and this will be cube A, we'll call it. And over here I have one that's kind of exploded, a little bit larger. And let's say that these sides are 2 centimeters. So we're looking for a linear measurement here. The question that's being asked, let me look in the book here, is how many times, let's see, the linear measures are how many times larger in cube B than in cube A. So I'm going to look at just the side here. That's a linear measurement because it's just 1 centimeter long on the cube A, and on the cube B, it's 2 centimeters long. So what is the scale factor? Well, the scale factor is 2. Think about that. 1 times 2 will give me 2. So the scale factor is 2 for our linear measurement of that side. Okay, now let's look at another example here. I'm going to draw some rectangular prisms for you. I'll do those in red just to change up the color a little bit. Okay, and on this one I have 3 centimeters across the bottom, 2 centimeters in, let me look here. Yeah, 2 centimeters in height. And then going back here is 4 centimeters. Okay, and then I have another one over here that's larger. I'm gonna have to probably draw it down here a little bit. Yikes. Okay, so I have, this one is 9 centimeters across the bottom and 6 centimeters in height and 12 centimeters in width. Yes, okay. So there's my 2 rectangular prisms. So we're going to figure out what the scale factor is for the linear measurement. We're going to find out how much, do we call this? Times. And we're going to figure out how many times the area of a corresponding face is, and then also for the volume. So we have 3 different things we're going to be looking at between these 2 red rectangular prisms. So the scale factor for the linear measurement, can we tell? I can look at any one side. I can look at these right here. I can see that that side, those are corresponding sides, and that's 3 times the measurement, right? Because 2 times 3 would give me 6. And then I also have, I can look at this one just to kind of double check it. I could go from 4 to 12, and that would be 3 times bigger as well. And then finally, I could look at the last one down here and notice that, again, it's 3 times larger because 3 times 3 would give me 9. So the scale factor is obviously 3 on our linear measurement. That's a linear because we're talking only about the sides. So my rectangular prism on the right for the length of my sides is 3 times larger on my larger rectangular prism. But the second thing I want to do is I want to figure out how much larger the area is on one face. So what is one face? Let's just look here. So the face would be this, let me shade it in here. That would be a good idea so you could see it. Let's use yellow. So here's one face. And on this one, here's a face. All right, so what is the area of that face? We would have 2 times 3, right? Because here's the measurement. 2 times 3, and I would get 6 centimeters squared. Okay, so that's the area of one face. And the area of this face would be those same 2 measurements, but 6 times 9 would give me 54 centimeters squared. Well, how much larger is 54 than 6? That's 9 times larger, isn't it? So I want you to think about something. We're going to look at a relationship here in just a minute, but I want you to kind of be thinking about how we're getting from our scale factor to the area to the volume. So let's look at the volume. So the volume is going to be how many little cubes can fit inside each one of these rectangular prisms. So let's figure out the volume. I'm going to do that one in a different color for you. Let's use green here. So the volume is going to be the 3 measurements multiplied, 2 times 3 times 4, and you're going to end up with 24 centimeters cubed volume. And on this one, you're going to have 6 times 9 times 12. And when I did the math on that earlier, it's 648 centimeters cubed. Now that's a pretty big number, but I'm looking to see what is the increase here. So how would I do that? So I'm going to go off to the side and how can I figure that out? That's kind of a big number to calculate. So now I'm going to come back down here and I'm going to ask you, using the scale factor, how could I have gotten from this to 9? You should probably say I would do 3 times 3, and you're absolutely right. So if I square, now I'm talking area, and you know whenever we have area, we always have this squared up here. So if I take my scale factor and I square it, I get the increase, how many times bigger my larger rectangular prism is than my smaller. Now think about that. If that's the case for area, what do you think I would do for my volume? I'm going to use the scale factor and I'm going to multiply it 3 times so that I have 3 to the 3rd power. That's what I use to figure out how many times larger the area is on my larger rectangular prism. It is 27 times larger. How do I know that? Well, I'm going to take this 24 and I'm going to multiply it with 27 and see if I get this right here. So down here, I'm just going to take 24 times 27. Let's see, and you can be working this out on your own on a piece of paper if you'd like to too. So I have 28, 14, 15, 16, 0, 8, and 4. And I get 8, 14, check it out, 648. So the 27 represents how much larger, how many times larger my larger rectangular prism is than my smaller one. Okay, so that's a lot of examples today. You're going to see one in your notes like this. I think I might get this put onto Edmodo so you can see the rest of those notes, because that's not in your notes for you to see, so I'm going to make sure that you have that. Okay, guys, that sums everything up for today. I will be seeing you soon on a Zoom call, so have fun trying to do some of the problems, and hopefully you can get quite a few of those done. I'm also going to post a link to a video if you have a chance to watch that. It's about a 10-minute video. It's kind of a cartoon one with a gal whose name's Scale Ella. So you're going to be seeing how she's going to be helping people fix their problems in the city through a cartoon character where you're going to see scale factors taking place. So take some time to watch that if you can. I wanted to show it during class, but it is 10 minutes long, and I know our time is valuable. So if you get a chance to watch it before meeting on Zoom, that would be great. If not, and we end up with time left, we will watch it together. Otherwise, you can watch it later, but it is kind of a fun little video to take a look at. All right, guys, I'll see you soon. Thanks for watching.